Hi everyone, so welcome back to yet new video on this segmentary series. So today in this video we'll be discussing about this interesting Codeforces problem from its EDU section that goes by the name first element at least x. So before continuing in this video, if you have not yet subscribed the channel, please consider subscribing it, and I'm already creating a lot of amazing contents as you can see, and I'm very sure that these videos will definitely help you in your interviews. So yes, if you have not yet subscribed, consider subscribing and share with your friends who need to watch these videos. Now let's come back to the problem. So this is the problem. So in this problem, you need to add to the segment tree the operation of finding the minimum index j such that a of j is greater than or equal to x. So in the input we will just be given two integers n and m. So this n will represent the size of the array, right? And this m will represent the number of operations or the number of queries. And then in the next line, it contains of n integers, that is the array itself, and each value can go up till 1e9 and the minimum value is 0, so every value is positive. In the next following lines, it contains the description of each query. So if the query is of first type, so it will contain two integers, that is I and v. So it means that we have to do the point update at this index I with this value v, right? So we have done this thing many times in the past, so this is not a harder thing, right? And this is the second query. So in the second query, we will just be given an integer x. So for this, we have to find the minimum index j such that a of j is greater than or equal to x. And if there is no such element, print -1 and indices start from 0. So we have to check for the whole array here, right? And for each operation of the second type, we have to print the answer for the query. That is for this query. That is the minimum index j for which this condition is satisfied. This is the problem, and in the input here, as you can see, the size of the array is 5 and the value of number of queries is 7. So this is my array, that is 1, 3, 2, 4 and 6, and then we are given 7 queries. So this is our first query, this is my second query, this is my third, this is fourth, this is fifth, this is sixth, and this is seventh. So every query will be either of the type 1. So every query will be either of the type 1 or either it will be of the type 2, right? So if it is of the type 1, then we don't have to do anything, but we just have to do the point update, right? That is, so we'll just say that t.update I comma v. That is, we have to change the value at the ith index equal to v. So this is an easy thing, right? We don't have to worry about this here. This problem mainly focuses on this part, how we will implement this logic. And for each of this query, we also have to print the answer, that is the minimum index j. So if I explain you the example here, please see. So this is our array, right? So in the first query, it is 2, 2. That is, the value of x here is 2. For the whole array, we have to find the first index or the minimum index for which the value is at least 2. So if we start checking one by one from the very start of the array, so this is my first element and it is equal to 1, which is less than 2, right? So we will move forward. So now we are currently present at this, and the value of this element is 3, which is obviously greater than this x. So since in this array we wanted to find the element which is at least 2, that is greater than or equal to 2. So this is the first element in this whole array when we started traversing from the very start, which is greater than or equal to 2. So what is the index of this element? The index of this element is 1 here clearly. So that's why the output for the first query is 1. Similarly, in the second query, which is represented by this integer, the value of x is 5. So it means that we want to find the index of that element for which the value is at least 5 and it should be the minimum in the array. So if you start traversing from here, then so this value is equal to 1, is less than 5, right? So it means that we will move forward. Now the value is 3, but it is less than 5. So we will again move forward. Now we are at the second index and its value is 2, which is still less than 5. So we will again move forward. And now we are at the third index, which has a value of 4 and it is still less than 5. So it means that we will again continue moving forward. And now we are at the last index, that is the fourth index, and its value now is equal to 6, and clearly our 6 is greater than or equal to 5, right? So the minimum index for which this query will give the output is the fourth index. So that's why the output for this query is 4. And now in the third query here, so this one represent that the query is of the type 1, that is the point update. So in the second index we have to replace whatever value present here before with 5. So let me change this here. Okay, so the value of this array is now 5 here for this index, right? Let's move to the fourth query here. So in the fourth query, it is of the type 2. That is, we have to find the minimum index for which the value is at least 4. So if we start traversing from the start, then it is 1, which is less than 4. So we will move forward. And now it is equal to 3, which is still less than 4. So we will again move forward. And now the value is equal to 5, which is clearly greater than or equal to 4. So we'll stop at this point. And what is the index of this element? So the index is 2, right? So that's why the output here is 2. So in this way we have performed this query now. Let us now move to this query. So now for this query we have to find the index in this array for which the element's value is at least 8. So let us start from the very start. Its value is 1, which is less than 8. So we'll move forward. So now we are at the first index, which has a value of 3, which is still less than 8. So we'll again move forward. And now we are at the second index, which has a value of 5, which is less than 8. So we'll again move forward. And now we are at the third index, which has a value of 4, which is less than 8. So we will again move forward. And now we are standing at the last index, that is the fourth index, which has a value of 6, which is still less than 8. So we will again continue moving forward. But after this element, that is the last index, we cannot go anywhere, right? Because this is the last element. So since we did not get any element in this array for which the element's value is at least 8 here, so for this the question has instructed us to print -1 if you have read. So here as you can read, we have to print -1 if there is no such element. So that's why the output, if you see here, it is minus. And now let us do our last second query. So in this query we have to do the point update at the third index equal to 7. That is, we have to change this 4 equal to 7. So let me do that quickly for you. Okay, so I have changed it now. So as you can see that this is the status of my current array after performing this query. And now let us perform the last query of this input. So for this query we have to find the minimum index for which the element's value is at least 6. That is greater than or equal to 6. So let us do the same thing here from the very start again. So this value is equal to 1, which is less than 6. So we'll move forward. And now this element has a value of 3, which is still less than 6. So we'll again move forward. And now this element has a value of 5, which is still less than 6. So we'll again move forward. And now we will stop at this point. Why? Because this has a value of 7, which is clearly greater than 6. That is greater than or equal to 6. So now what is the index of this element? It is 3, right? So that's why the output here is 3 for the last query. So in this way, we performed each and every query given in this input and got the correct outputs every time. So I hope you have understood the question very clearly, right? So the question is not asking us to do very difficult things. It will use a very simple concept of segment tree here. And please keep in mind one thing, the solution that I will explain to you in the blackboard will be a general solution. That is, for this question if you have read, then it has asked us to find this condition, that is a of j greater than or equal to x, for the whole array. That is, this j here can be any index from the starting to the end, right? But I will describe you a solution for which this j can vary. That is, you can even supply some range in the input from L to R, such that we will only be allowed to pick this j from that range only and not the complete range. And that will be more general and moreover a good question over this, right? So in this question the range is fixed here, that is j can be any value in the index range. But if the input has given you such that you have to select a j in a range only, that is from L to R. So I will describe you that solution only, and by putting the value of L as 0 and R as n-1, you can just submit this solution and it will give the correct answer. I hope you got this point. And why I have decided to make a video on this question here, because this is a very standard question and this concept will be used directly in many of the leetcode problems and the context problems. So that's why this concept is a very standard concept and it is applied in most of the problems. So let us now go to the blackboard and see how this question will be solved using segment tree. So I hope that you have tried to implement the brute force approach by yourself here. So I am not going to implement the brute force here because it is very easy to implement in this question, and by doing it yourself you will understand why that will give TLE. So that's why I will just discuss the optimal approach in this video. So if you remember, this was the given input in the problem, and this was the expected output. So the array given was this. So let me write this array outside here clearly. So the array is 1 3 2 4 6 and the indexes are 0 based, so 0 1 2 3 4. So this is the given array, right? So how we will solve this question using segment tree? So we know that since we have to just write a query function which will return me the minimum index for which the value of the element is at least x, right? So we have to write the query function in the segment tree template. And we know that whenever we write a query function, we always start from the root node of the segment tree. And please keep one thing in mind, that we know that a total number of nodes present in a segment tree is 4 times the number of total nodes in the array. So here, since n is equal to 5, so the total number of nodes that should be present in the segment tree here should be 20. But I have only drawn a total of 9 nodes here. That is, and I think these 9 nodes should be sufficient in answering the answer for each and every query. And other nodes will only act as the redundant nodes and it will not contribute to our answers. So that's why I have not drawn that. So now what I was saying was, we know that for each and every query function, we always start from the root node of the segment tree. And this is the root node, and the nodes that I have marked green color with in the side, so those nodes represent our base level or the leaf level, and each of these leaf nodes represent just one single element of the given array, right? So this represents the 0th index element, this represents the first index element, this represents the second index element, this represents the third index element, and this represents the 4th index element. So this is the basics, we know it already, I guess. And now, since we want to calculate the minimum index for which the value will be at least x for a given query. So now what I am telling you to do is, I guess you must have studied how to find the maximum in a range for using a segment tree, right? So we know that when we want to find the maximum in a range, so how we used to build the segment tree for this? So it is very simple. So we recursively travel to the left part of the tree and the right part, and then combine the left and right results into the parent each and every time, right? So we know this. So let us do the same thing here also, and you will very soon realize that how finding the maximum for each and every range here in this nodes will help us in answering each and every query. So let us do that quickly here. So since this is 3 and this is 1, it means that the maximum for this range, that is this 0 to 1 range, should be equal to the maximum of the left child and the right child, which is 3 here. So this will be 3. Similarly, the maximum of this left child and this right child will be the maximum of this. That is maximum of 3 and 2, which is 3 obviously. So this will be 3. And once we have explored the left part completely, now we will go to the right part. So now we are present at these two nodes. It will now find the maximum of this part and this part. So it is 6, right? So it means that the value of maximum for this range is now 6, which is coming from this right child. And now once we have got the result of this left and right child, we will combine this into the root node, that is the parent node of these two nodes. So what is the maximum of this 3 and 6? It is 6, right? So I will write here just 6. So in this way we have built our segment tree from the bottom to the top, such that each node is storing the maximum of that range, that is the maximum element present in that range in this array. You can verify this also, so I think I filled this correctly here. And now, as I was telling you before, that since in this question we just have to write a query function that should be capable of answering each and every query, right? So we know that for every query function we always start from the root node of the tree. So now let us finally start doing the procedure here. So now we are standing at this root node, and this is the range here for this root node, which is from 0 to 4, that is the whole array. And for this whole array, the maximum element is 6. So for this range, the maximum element is 6, which is here. So now let us perform each and every query one by one. This is the first query, that is 2, 2. It means that the query is of type 2 and the given value of x here is 2 also. So x is here 2. So as I have told you before, that in this question we have to find this minimum index j for this whole range. That is, this j can be between this 0 and this n minus 1, right? So there is no specific range given in the question. We have to find it for the whole array, that is our j value, that is the minimum index that we have to answer for each and every query, can be any value in this range. That is, we always have to check from the very start of this array and check one by one which is the first element, which is at least x, right? So there is no bound on the left and the right part. So we have to check for the whole array here. So if I write that here, so it means that my L value is 0 and my R value here is n minus 1. coming back to the problem, so I was telling you that we were standing at this node and this was the range, and for this range the maximum value was 6. So the maximum value for this range was 6, which was coming from here, right? So this was our first query, that is 2 comma 2, that is we have to find the minimum index for which the element's value is at least 2 here, that is x. Just assume for a moment that instead of this x equal to 2, I was given to solve this x for x equal to 14. So what would be the answer for this query in that? That is, I would have wanted to find that index for which the value was at least 14 in this. But clearly, in this whole array, the maximum value was 6 only, and there is no value of 14. So if there is no index possible to find for a particular query, so in that case the question has asked us to print -1, right? So if my x was 14 here in this case, then I would have just printed -1, because the maximum value present in the whole array is just 6. So there is no index for which the element's value will be at least 14, so -1. So that's why whenever we'll be present at any node, at this current node, we will always check that what is the maximum value present in its current range. So since for this node here the maximum value is 6 here, and since we wanted to find such element whose value is at least 2, it means that this range definitely contains some index, that is some base level index, for which the value is at least 2, because the maximum value is 6 here, right? Maximum value for this range is 6. So there is definitely some index present in this range for which the value is at least 2 here. So it can either be present on the left part or it can either be present on the right part. We are not sure. By currently standing here, we are just not sure that whether to go to the left part or to the right part. Thereby, it means that we have to explore both the parts. So first we will explore the left part and then we will explore the right part. But since we know that this node is represented by a value of node, and the left child is represented by a value of 2 into node plus 1, and the right child is represented by a value of 2 into node plus 2, right? By currently standing at this node only, we can know the value of this node and this node, right? Since we want to find an element for which the value is at least 2, so by standing here only, before actually going to the left part, we will check that what is the maximum value present in this whole left part, that is in this range, which is present at this node, which is 3 here. So the maximum value present is 3, which is definitely greater than this x. So it means that there is some index in this range for which the value is at least 2, because the 3 is the utmost value for this range. So it means that it is feasible to go to this part, that is to the left part. So that's why I will go to this left, and now I am standing at this node. So again we will do the same thing as I did in this node, that is I will check what is the maximum value present in the current node for this range. So since this represents from 0 to 2 and the maximum value present in 0 to 2 is this 3, right? And we wanted x at least 2, that is greater than or equal to 2. It means that in these both parts there is some index for which the value is at least 2, right? But we are not sure as of now whether it is present in the left part or whether it is present in the right part. So that's why we'll go first to the left part. But as I said here before in this case, that whenever we'll be standing at some current node, we will directly before actually moving determine if it is feasible to go this part or not. Similarly, since we were currently standing here, we will just determine by standing here only that if it is feasible to go to the left part or not. That is, the maximum value present in this range, we will check, and it is 3 here, and we wanted to find the index for which the value is at least 2. So it means that there is some index in this range here for which the value is at least 2. So this range, which ultimately represent these two base level indexes, contains some element which is greater than or equal to 2. So that's why it means that since I was standing here, I would definitely go and explore the left part, because I know that its value is 3. So there is some element in the base level for which the value is at least 2. So it is feasible to go to the left part. So that's why I will move to the left part now. And now, since I was present at this node now, we will see the range of this node. So it is 0 to 1, and the maximum value for this range is 3. And we want x to be at least 2, that is greater than or equal to 2. So it means that there is some index in this range for which the value is at least 2. So it is feasible to actually explore this part, right? but we are not sure by standing here that whether to go to the left part or to the right part. So by standing here, we will first check if it is feasible to go to the left part. So that's why by standing here, I will check the node value of the left. So it is 1 here. So since the node value here is equal to 1, that is the maximum value present in this range is 1 only. But we wanted our x to be at least 2, which means that clearly we don't want to go to this part anymore. Why? Because this part, which represents a range from 0 to 0, has a maximum value of 1. So we will not get any index with an element at least 2. So that's why I will not go to this part. And even if I go to this part, I will return some value that will be ignored here. So now, after exploring this part and not getting any result, the only option that we are left to explore is this right child, right? And since by standing here earlier, we saw that there is some element in this range which has a value of at most 3. And that element is obviously not present on this side, so it means that it will definitely be present on this side, right? So that's why we will now explore the right part of this. So now I am standing at this node, and since now I am standing at this node, and for this node clearly it has a value of 3 which is greater than or equal to 2, and also for this node this is a base level node. How we will know this? Because for this node our start is equal to end. So if this is true, then so it means that we have finally found that one index, that is the minimum index for which the value is at least 2 in this whole range here, which is this index, that is 1. So we will just print or return this. So that's why the output here is also 1. So in this way we are done with the first query here. Let me erase this now. Okay, so now I want to perform operation for the second query. That is, I want to find the minimum index for which the value is at least 5. So if you look here blindly, then in this array the minimum element for which the value is 5 is this element only, that is the 4th index. So that's why the output is 4. But how we will determine using the segment tree? Let's see. So as I told you that for each and every query we will only start from the root node only, because this is how the query function works. So now we are standing at this root node, and for this root node it represents this range, and the maximum value present in this range is this 6. And the value here that we want, so let me write here also. So now we want at least 5. So our x is 5 here. So since this range has a maximum of 6, so it means that this definitely contains a base level index for which the element value is at least x, that is greater than or equal to 5. So it may be present on the left part or it may be present on the right part. So if we are able to find the answer on the left part, then we will not need to explore it on the right part, because the question wants us to answer the minimum index. So it might be present on both the sides. That is, there can be some value which is greater than or equal to 5 and might be present on both the sides of this tree, but since we want to answer the minimum one, so that's why we will only go with the minimum that we found, and that's why we will not explore this other part. Okay, so now let us start doing this. So since I was standing at this node and it had a value of 6 which was greater than or equal to 5, so it means that there is definitely some node present either in this part or maybe in this part or maybe in both the parts for which the value is at least x, that is 5. So since we are not sure here, so we will try to move in both the parts one by one. But before actually moving to the left part, I will first check here that if it is feasible to actually go to the left part. And how we will determine this feasibility? So now the maximum value present in this range here is 3, which is represented and written in this node. So since this range has a value of 3, but we want such element which has a value of 5 at least. So it means that there is no element present in the base level of this part for which the value is at least 5. So all these values will be less than 5 here. So it means that it is not actually feasible to go to the left part. The only other possibility that we are left now to explore is this right part. So that's why now I will explore the right part of this segment tree, and I am standing on this node which represents this range and it has a value of 6 here. So since this range has a maximum value of 6, it means that there are some base level leaf nodes of this tree for which the element's value is at least 5. Because since the maximum value is 6, I just want some index greater than or equal to 5 here. So there is some element definitely present in the base level for this whole tree, right? But we don't know as of now whether it is present in the left part or the right part. So I will want to explore both the parts. But before actually exploring the left part, I will check if it is feasible to go to the left part or not. This represented node and this represented 2 into node plus 1 and this represented 2 into node plus 2 as I told you before. So I will just check here by only that what is the value of the left child. So since the left child has a value of 4, it means that the range that it is a part of has a maximum value of 4. But since I wanted that element which has a minimum value of 5 at least, so it means that if we explore this part of the tree, then whatever value we'll get at the base level will be maximum 4 only and will not be greater than or equal to 5. So it means that it is not feasible to explore the left part. And that's why we will never explore the left part and we'll go to the right part only. And that's why I will explore the right part now and will be standing on this node. So this has a value of 6. And since this has a value of 6 here and I have reached this node successfully, and for this node clearly the value is 6 which is greater than or equal to 5 here, and for this 6 node also our start is equal to end, which means that we have reached the base level successfully. And since we done this without any problem, so that's why it means that this is the minimum index for which our element's value is at least this. So we will just return or print this 4. So that's why if you see, then the output is also 4. So in this way we did the second query also. Let us now move to the third query of this problem. So the third query is a point update. That is, we have to update the second index equal to 5. So since this third query is about the point update here, so here we have to change this 2 equal to 5. That is this second index equal to 5 here. So I have changed this equal to 5, and now I also have to change this and update it in the segment tree here, right? So since our second index is located here, so that means I will change this 2 here equal to this 5. And by doing this, we know that whatever nodes are present in this path from the bottom till the top, those much nodes will also change. That is, I have changed this node already, so this will also change now and this will also change. And since in each of the node I am just storing the maximum of the left and right child, so for this node now it will contain the maximum of these two, that is maximum of 3, 5, which is 5, so it will be 5 now. Similarly, this node will contain the maximum of these two, that is maximum of 5, 6, which is 6, so it will store 6 now. So in this way I have updated the segment tree from the bottom till the top, and by doing this I also have completed the third query. So let us now move to the fourth query here. So the fourth query is 2, 4. That is, our x value is now 4. So it means that we have to find the minimum index for which the element's value is at least 4. So let us start performing this query here. So as I said that for each and every query we always start from the root node. So as we can see that for this root node it has a maximum value of 6. So there is some element present at the base level for this tree for which the value is at most 6, that is greater than or equal to 4. But we are not sure whether it is present in the left or the right part, so we will explore both the parts one by one. And if it is possible to get it from the left part, so we will not explore the right part. But if it is not possible to get it from the left part, then we will get to the right part. So now we are standing at this point and we want to move to the left part. But before actually moving, we will just check what is the maximum value present in the left part, that is this part of the subtree, that is this range here. So the maximum value is 5 here only. So it means that it is definitely feasible to go to the left part. So now I am standing here. Now it has a value of 5 which is clearly greater than or equal to 4. So there is definitely some element present in this part, that is the base level node, for which the value is at least 4. So just by standing here, I will first check that what is the maximum value present in the left part, that is this range, So it is 3 here. So since this range has a maximum of 3, the minimum value that we wanted is 4. So it means that we will not get any element in this range for which the value is greater than or equal to 4. So we will not want to explore this part, and thereby we will only explore this part, that is the right part here. So that's why now I will be standing at this node, and since now I am standing at this node successfully without any problem, for which start is equal to end, and also the current value is obviously greater than what we need, so it means that we have got our answer, which is 2 here. So we'll just return this 2, and this is our output here also, if you see. So in this way we have also performed our fourth query. Now let me erase this. So now let us perform our fifth query here. So this is our fifth query, that is 2, 8. That is, our x value is now 8. So now it means that we want to find the minimum index for which the value is at least x, which is equal to 8. So as every other query, we will again start from the root node. So now if you see clearly, this node has a value of 6 which represents the maximum of this range, that is the maximum of this range, which is 6. In this whole array, I want to find the minimum index for which the value is at least 8. But since this whole range here has a maximum value of 6, So it means that we will not get any index for which the element value will be at least 8. Common sense, right? So even if we go to the left part or even we go to the right part, we will not get any element at the leaf level for which the element value will be greater than or equal to 8. So it means that there is no benefit for us for going to the left part or to the right part. For this case, we'll just return a -1 directly. Now let us perform our last second query here. So for this query, we have to change the third index equal to 7. That is, this index equal to 7. So if I do it in the segment tree here also, so the third index is located here, which has a current value of 4. So I want to erase this 4. And I know that if I change this 4 equal to 7 now, so by doing this, I also have to update the nodes present along this path here. So the new value for this node will be the maximum of these two, that is maximum of 7, 6, which is 7 here. Similarly, the maximum of these two will be present here now, which is 5, which is the maximum of 5 and 7, which is 7, so 7 here. So in this way, I have updated my segment tree again and have successfully done this query, that is the point update query. And now if I do the last query of this input, that is 2, 6, so now my x is equal to 6 here. So since my x is equal to 6 here, so let us begin our process. So I'm standing at the root node initially, and if I saw in the range that what is the maximum value present in this range, then it is 7. I want a value which is at least 6, that is greater than or equal to 6. So it means that there is definitely some base level index which has a value of at least 6 here. So it may be present in the left part or the right part or both the part. So that's why we'll first try to explore the left part since we want the minimum index. But before actually moving it, we'll first see what is the maximum value present in this range. So the maximum value present in this part of the segment tree is 5. That is, for all these leaf nodes, the maximum value of them is 5. But since we want to find an index for which the minimum value is at least 6, so it means that there is no element present in this part of the segment tree that satisfies this criteria. So we will not explore this part. So the other possibility that we are left to explore is this right part. So now I will move to the right part and will stand here. So now I am standing here. And now if you see, then the maximum value present in this range is 7. Since my x is 6, that is, I want my leaf level index element to be at least 6. So it is definitely possible either in this part or both the parts, right? But since we want the minimum, we will first want to explore the left part. But before exploring, I will just check from here that what is the maximum element present in this left child. So since the maximum element present in this left child here is 7 only, which is definitely greater than or equal to 6. So that's why it is feasible to move to the left part actually. And thus I will move to the left part and will stand here. And since I have reached a leaf node such that my start is equal to end, right? And it had a value of, and it has also a value of greater than or equal to x here. So I have got my answer here, which is 3. So I'll just print or return. So in this way, we did each and every query as given in the input and got the correct outputs every time. But as I told you that in this question, the work was made simple because this L was given 0 and this R was given n-1. That is, we have to find the minimum index for this whole range. But when you will solve some questions from other platforms, then they will not allow you to select this whole range directly. That is, what I am trying to say is, instead of this 0 and -1, you will actually be given some L value and R value. And in that particular L to R range only, you have to find the minimum index J. That will satisfy the given query. So how we will solve that in this case? So the approach will be exactly same. So along with doing these things, I will just add a few checks. So suppose for the first query, suppose now for this first query here, that is 2, 2, that is our x is equal to 2. And just assume for a moment that our L was equal to 1 here and R equal to n-1 only. That is, we wanted to find the minimum index J now for this range. So that's why when I will start my query from here, so earlier I was just checking in the left part what is the maximum value, and by comparing this maximum value with this given value of x, I was able to determine if it is feasible go to the left part or not. But now since this L is also given, so it means that this range here, that is from 0 to 2, might or might not contain this L. Suppose instead of this 1 here, my L was 3 actually. That is, I had to find the minimum index J for this range, for this query. The condition that I was checking before is that the node value should be at least x here, which is true. So there is definitely some base level node here which is at least x, that is 2 here. So earlier we were just moving to the left part by checking this, but since now this L is also given, so it means that there might be some node present in the leaf node which is at least x, but it might not fall in this range, that is 3, 4, because this part of the tree represents this range, that is from 0 to 2, that is this. But since now I want to answer the query starting from the 3 here, that is this. So even if my this part contains a element which is at least 2 here, which is at the first index here, which is here only, even if this is present, I will not explore this part, that is this part. Why? Because this lies outside of what we are allowed to do. So that's why now I will not explore this left part and will only explore the right part. And now if I go to the right part, then clearly this is 3 to 4, right? And since this 7 has a value greater than or equal to 2, obviously, so the first condition is satisfied. And the second condition that I told you now is that this range, which is from 3 to 4 here, so our L is 3, that is we want to select the indexes greater than or equal to 3, which is true here for this part of the tree here, right? So that's why it is actually good to go with the right part. That's why this is a significant difference from the previous approach that I told you. So in the previous I told you that when the L and R was not bound here, we were just checking whether the left summation is at least this x or not, and if this was x, then I was just moving to the left part. But now I am also checking that what is this value of L. So if this value of L lies completely outside of this range here, so it means that we don't want to explore this part even if some value is present here that satisfies this x. So now I discussed a case when this L was present outside of this range. So let us now change this case here a little bit, and let's say that our L is 1. We'll do the same thing again. So now I'm standing here and I know that I'll first check the left part and the right part. So clearly this 5 is greater than or equal to 2, obviously, so the first condition is satisfied. But the second condition is that this L should also present in this range, and here if you see, then our L is 1. So since this represents a range from 0 to 2, that is from 0, 1, 2, and since I was allowed to select the range starting from this 1 also, right? So it means that these two indexes, that is 1 and 2, can be our possible answers. So if I write that here, so what I'm saying is this represents 0 to 2, right? And I was allowed to take any range starting from 1, that is of this part. There can be two possibilities, that this 5 might be present in this part or might be present in this part. We don't know that still, right? But it is sure that it is definitely present in some part of this range. So that's why we will try to explore the left part, independent of whether we will be finally able to get that result or not. And since now I'm standing at this, and since it has a value of 5, so it means that there is some base level leaf node which has a value of at least 2, because the maximum value is 5. So it can be present in either the left part or the right part, but we don't know. So we'll first check the left part. But as I told you that instead of checking one condition, I will check two conditions. That is for the maximum value of the left child and this range and the L value comparison. So since the maximum value is 3 here and I want a minimum value of 2, so it means that we can get this in this part here easily, right? The first condition is satisfied, but the second condition was that this L should be present in this range if you want to explore the left part. So what is this range? It is 0, 1. So now this represents 0 to 1, right? And since we were allowed to take any index from 1 that is greater than or equal to 1, so here we can take this part of the array. So whatever this 3 value is present here, it might be present in this part or this, but we don't know yet. So that's why we will explore both the parts. So now I will go to the left part here and then the right. So once I go to the left part here, but before actually going, as I told you before in case of each and every node above, that before going I will just check here what is the maximum value present in the left part. So since the maximum value present in the left part now here is equal to 1, which is clearly less than 2. So it means that we will not get any node in this part of the tree which has a value of at least 2. So we will not explore this part at all. So we'll move to the right part. And now I'm standing at this node. And since I'm standing at this node now, for which it has a value of 3, it is greater than or equal to this x equal to 2, and for this also the start is equal to end, that is, it is a leaf node. So it means that we have found the minimum index that is satisfying both of the conditions. That is, for this range the minimum value is the maximum value is at least 2 here, and this L is also present in that range. That is this. So I'll just return one. So I really hope that you have understood whatever I have told you till now. And in the same way, as we are bound with this L, we can also be bound with this R. That is, we can be allowed to pick any index value j from a particular L to a particular R. So for this R also we will do the same thing only. That is, whenever we will be present in each and every node, then we will check if this range lies completely outside of this range or not. So if this range lies completely outside of this, it means that there is no benefit of exploring this whole part. So we will not explore that part and we will only explore the right part. So what I am trying to say is, suppose this L was my 3 and this 3 only, right? So it means that the only part of the range of this array that I was allowed to explore is this. We were not allowed to explore this part and were only allowed to explore the right part. And even we were allowed to explore this right part, now also if you see, then we cannot go to this right part because it represents a range from 4 to 4 which lies completely outside of this. So we will not get any answer from here and we will only explore the right part, the left part. Similarly, instead of this 3 3, if we were given 4 4 here, then it means that when we were present at this node, even if we try to go to the left part here, we will not go that part. Why? Because the range that was present there is clearly outside of what we want, so we will not go that. So I really hope that you have understood whatever I told you till now, right? So if you are still watching the video and have not subscribed to the channel, please subscribe the channel because it is already taking a lot of efforts to create each and every single video from my side. So I think it would be very better for us if we actually move to the coding part and actually code this up, and then you will understand each and everything how it is performing under the hood. And finally, whatever I said to you till now will actually make sense. So let us now go to the code editor and actually code this up. So in the input, we have to take the inputs of n and m and then n integers and then the number of queries, right? So and then the n integers. So this is my input of the array here, and now I have to actually iterate through the m queries given. So for each and every query, I first have to take the input of the type. That is, whether it is a update type or a query type. So if my type is equal to 2, then it means that this is a query type, right? And if this is not the case, it means that this is what? This is a update type. So for this array, let me declare the segment tree here. So I have also pasted my standard segment tree template here, and we have to write this query function, right? So before doing that, let us fill these parts quickly here. So we know for each query type, that is type 2, we will be given an integer x, right? So we'll say this, and for this we want to print the answer. So I will say t.query, and for each query I will pass 3 parameters, that is this x, the leftmost value L, and the rightmost value R. But as I told you that in this problem of the Codeforces EDU section, our L is equal to 0 and my R is equal to 1, sorry, n minus 1. So it will be this, right? And in the update query, we will be given 2 integers actually. That is the index which I have to update and the value with which I have to update. This index equal to this value, and at last just return. So after doing this, I think I have written the void function here completely. The only task we are left with is to write this query function. So we are provided with this x, L and R initially, right? So what I told you that whenever we will be standing at the current node, we will check its current value. That is the tree of node. So if the current value, what we want, I want this current value to be actually greater than or equal to the x. But if it is somehow less than x, then it means that I will not explore this anymore, because whatever the maximum value present in this range is not even x, so we will not get any answer. So I'll just return a -1 here. And I also told you that there is some restriction by this L and R. So if you are given a particular range from L to R, then I will also check that if my end value is actually greater than or equal to L or not. So if my end value is less than L, it means that we will again not get any answer from this node. And similarly from this right part also, I want that this right should be actually greater than or equal to the start. But if this right is actually less than start, so I'll again not get any answer. So that's a -1 for all these 3. And now if this is not the case, then it means that this is a valid node. So some answer is possible. So either we have reached the answer node, that is the leaf node, or we have to explore the further nodes. So I will just check if this is a leaf node or not. That is, if my start is equal to this end or not. So if it is equal, then I will just return the index here. Let's say end. You can also write start here, right? Because the start is equal to end here. And even if this is not the case, it means that we have to explore both the parts. So I'll just find a mid here, And what is this mid equal to? It is equal to nothing but start plus end by 2 here, right? So start plus end by 2. If you have noticed that whenever we will be calculating the mid value for the current node, so for here mid is actually 0 plus 4 by 2, which is 2 only. So this mid value will be actually the end of this left child. So that's why I will say here that if my tree of 2 into node plus 1, that is the value of the left child, is greater than or equal to x. So one condition, that is the first condition on the first condition on the node value, and then the second condition should be on the L value, that is if my mid is actually greater than or equal to L or not, that is if my L is less than or equal to mid or not. So if my L is less than or equal to mid here, so this is a mid here, right? So since this is my mid here, that is 0 1 2, this is my mid, and since what I'm saying is in this 0 1 2, if my L value is actually starting from this less than or equal to mid here, that is before this range, so it means that there can be some indexes possible, right? So we can't ignore that. So that's why I'm checking if my L is less than or equal to mid, so it means that there can be some possible answer in this left part. So we'll explore this left part, and whatever value it will return, I will just store this in a variable, let's say left operand value. So how we will explore this left part? So for doing this, we will only call the same function again. So instead of this node now, it is equal to 2 into node plus 1. Our start will be the same as the start, but our end will now be mid, and my x, my L and my R will remain same. If this value is not equal to minus 1, so this statement means that by exploring the left part, I have got some value which is not equal to minus 1. That is, I have got this value here. That is a valid leaf node index. So I just have to print that only, right? So I will say, or rather return this. So return this. And if this is not true, that is after exploring the left part, things never went true. So it means that our answer can now be present in the right part only, right, and not the left part, because when we explored the left part we got nothing. Since we got nothing, it means that the only option that we are left to explore is the right part. So that's why we'll just explore the right part like this. So this is how I will write this query function here, and I think I have done a very silly mistake here. So this will not be a comma but this, and also I think I should give here a handle here, because every time I have to print the output on a new line. Let's run the code and see if this is fine or not. As you can see, the outputs are correctly passing. So this is the code that we just wrote. So now let us try to submit this code and let's see if this is getting accepted into the platform or not. So as you can see that it is accepted successfully, and so this is the code that we just wrote and submitted and got it accepted on the platform. So I really hope that you have understood the concept very well, right? So this is a small concept that will be used directly in most of the contest problems, right? So that's why it is very important to watch this video and understand whatever I have told you. And yes, if you are still watching and have not subscribed the channel yet, please consider subscribing, because I am already creating a lot of amazing content, as you can see, right? And I am planning to upload more and more videos related to segmentary in the upcoming weeks. So yeah, thank you for watching this video. Thank you.